So we would like to give an analog of the binomial theorem for a completely different setup, which will involve some identities linked to the combinatorics of the Young diagrams that we talked about in the previous video. And at first, this theorem will look completely strange, even though it will bear some obvious analogy to the usual binomial theorem. In fact, as we're going to see, it will include the binomial theorem as a special case. So let's first of all give the statement because, the statement is already strange when somebody looks at it. So we have this, we have that 1 plus xq, 1 plus xq squared, all the way to 1 plus x to the x times q to the n is equal to a sum where we have these strange terms that we're going to explain in a second. They are polynomials of q times q to the k times k plus 1 over 2 times x to the k. So one could argue right away that by giving this statement, we already have something that looks very much like what one gets in the binomial theorem. In fact, when we define we haven't defined this quantity yet, but once we define it, we will see that if we let q approach 1, then we get the usual binomial theorem. So in any case, before we proceed to explain more what that means, let me just give you an alternative version that is very often available. I mean, so you will have 1 plus x, 1 plus xq, and so on, plus 1 plus xq to the n minus 1. That's equal to the sum from k equals 0 to n of n, this square bracket of n over k, times q to the k times k minus 1 over 2 times x to the k. So first of all, the two theorems, the two formulas can be easily seen to be equivalent, even if you don't know how this n over k bracket is defined. All you need to do in order to obtain, let's say from the second, the first one is replace x by xq. So if you replace x by xq in the first one, in the second one, then you get the first one. Okay. Or conversely, you could replace x in the first one by x over q, and you would get the second one. Okay, so now the question is, what is the definition of this n over m bracket? These are known as Gaussian polynomials. And we will see that they have a very interesting combinatorial nature that can be linked to Young diagrams. But let's not overflow ourselves with information at this point. And let's just say that this is defined to be 1 minus q to the n, and then the powers start descending till we reach 1 minus q to the n minus m plus 1. And on the bottom, we have 1 minus q to the m times 1 minus q to the m minus 1, all the way down to 1 minus q. This is how this is defined. And at first glance, this looks to be a polynomial, a rational function of Q, but actually turns out to be a polynomial in Q. And what is interesting is that if we consider this as a limit, you could even try to apply L'Hopital's rule here, but it's easier to actually do a little trick and divide by 1 minus Q to the m power, both numerator and denominator, and then pass to the limit. Regardless how you look at it, this is an exercise in calculus that this tends to n choose m as Q tends to 1. As Q tends to 1. And this is a paradigm of a very interesting trend where we have the common numbers and then we have the expressions of Q that tend to common numbers as Q tends to 1. And we have an analogy in the identities, and we're going to see that actually the triple product identity falls within the confines of such an analogy. It's a very interesting situation, and I'm not sure that we have a full grasp of what is going on. So there are some interesting things that are yet to be understood, but certainly there are some very interesting combinatorics that we're going to explore in this context. So this is the Q binomial theorem, which is in analogy to with the usual Newton's binomial theorem. And our job in the next few videos will be to explain the combinatorial nature of these polynomials and actually give a proof of this theorem. Eventually, we will see that a proof of the triple product identity can be based on this theorem. And that's all. Thanks for watching.